NERSC is the National Energy Research Scientific Computing Center.
We're really excited to have some of the most energy efficient computers in the world. We work very hard to make sure that the amount of science we get for the amount of watt of power we put into our systems is as high as possible. Edison is an incredibly efficient computer system, and it's pretty novel in a couple of approaches. First of all, they have the air moving transversely down the entire row, which is extremely efficient for us. It means that we're using the same air to cool each compute cabinet as it's moving through the system. With our previous generation, we had 22 air handlers. With Edison, we can do it with 2.
This eliminates an enormous amount of energy that otherwise goes into mechanical chillers or other things which do not directly support computation. If you think about it, you want all your energy to be going directly to the computation associated with the machine.
And then that heat is directly captured through a radiator that sits between each of the compute racks. So the energy transfer and heat transfer directly into the water system is extremely efficient for us. We've got the entire cooling loop now down to right about 15 kilowatts of power use compared to a 2.5 megawatt compute system.
The Berkeley Lab has been really at the forefront of trying to understand how energy is used in computing centers, from cloud centers and data centers used in business to high-performance computing centers like NERSC. The purchase of Edison has really moved us forward in terms of the energy efficiency that we can get. And we look at this from a very unique perspective, which is I would like to understand how many joules of energy is required to solve a particular scientific problem.
Without high-performance computing, we really could never have put together the realistic physics associated with both chemistry and flow.
We exercise the whole system. Currently we're working on full focal plane 7, and that we did in 2 nights on Edison.
You can see all of the nooks and crannies and the striations. We have been selling this as mesoscale science meets extreme computing.
It's just so exciting to be able to have this technique where we can image things in 3 dimensions and look inside of objects without having to break them open and use that to make 3D simulations and 3D models of things. It's just a lot of fun.
And what we've seen is that Edison is, on average, about 5 times more energy efficient in terms of the amount of actual application-level work that you can get done relative to even the Hopper system, which was already a significant improvement over the past.
So we're very excited about our new building, the Computing Research and Theory Facility that's being built up on the hill right above campus. It'll go into production in 2015.
We've built it on a hillside so we can use the bottom underside of the data center as the air plenum. So we take outside air from the San Francisco fog banks that are constantly blowing into Berkeley. We treat it and make sure it's clean, then pump it directly into our data center where it will flow through our supercomputers. And then we take the hot air afterwards and either eject it out of the building, or on the really cool days, we use it to heat the entire office floors.
Edison also is a very energy efficient system. We're already finding that it's using a lot less power than we had anticipated, and that's due to all the dynamic power management that's going on. So the system will automatically adjust itself to use less power if applications don't require it to run everything at full speed. So it'll slow down parts of the system to conserve power.